Hello and welcome to a new video on IGCSE Physics. In this video, we shall be discussing motion graphs. This is from classified paper 4 questions. So let's begin. We will begin with sketching graphs. A boat is moving at a constant speed. Sketch a distance time graph for the boat. So you should know that for a distance time graph, the speed represents the slope. And the slope is constant here because we have constant speed. So if we have a constant slope, this means that the graph is a straight line. So therefore, we expect the graph to look something like this. It is possible also to start at a different point, that doesn't matter, but any upsloping line would be correct. And therefore, the correct answer here looks something like this. A car accelerates uniformly from rest at 2.2 meters per second squared for 3 seconds. Sketch a distance time graph for the first 3 seconds of the journey. So we said that the speed is the slope, and the fact that the car accelerates, this means that the speed keeps on increasing. So therefore, we expect the graph to be nonlinear because the slope here is not the same, it's not constant. It's a curve because the slope keeps increasing. So it will be an upwards concave curve that looks like this. So therefore, the correct answer will be something that looks like this. A rocket is stationary on the launch pad. At time t equals 0, the rocket engines are switched on and exhaust gases are ejected from the nozzles of the engines. The rocket accelerates upward. Figure 1.1 shows how the acceleration of the rocket varies between time t equals 0 and time t equals tf, excuse me. A says define acceleration. So of course, the definition of acceleration here is the change of velocity per unit time. And we should know that there is a very famous equation, v equals u plus at, or actually in another sense, a equals v minus u over t, where v is the final speed and u is the initial speed. So therefore, v minus u would be the change in speed or the change in velocity, more accurately, divided by the time. So we say per unit time, and this is very important. You cannot just say it is the change in velocity or the increase in velocity. You have to say it's the change of velocity in 1 second or per unit time. Now for the second part of the question, we're told on figure 1.2, sketch a graph to show how the speed of the rocket varies between time t equals 0 and time t equals tf. So in figure 1.1, the acceleration is increasing. The acceleration is not constant. So since the acceleration itself is increasing, we should know that the acceleration here is the slope of the speed time graph. So the speed itself is not constant here. So from here to there, in this first section, the slope is changing. So since the slope is changing, we should know that the graph is nonlinear. So we have a concave up curve like we did in the last problem. But then in the second part of the problem, we have a constant acceleration. So in this case, the slope is constant. So if the slope is constant, then the graph itself has to be a line. And since the slope is positive, so the line has to be sloping upwards. It has to be an upward slope line. So therefore, the final graph should look something like this, where for the first part, it's concave up as a curve. And then for the second part, it's linear in order to reflect the graph on the left. A bus travels at constant speed. It stops for a short time and then travels at a higher constant speed. Using the axes in figure 1.1, draw a distance time graph for this bus journey. So the answer will look something like this. In the first phase, the bus travels at a constant speed, and we said that for distance, the speed is the slope. So the speed here is the slope of this graph, and it's constant, and constant here would mean that the graph is linear. So we draw a line for the first part, just any upsloping line like this. And then it stops for a short time. So therefore, the slope will be 0 and the line will be horizontal. The distance will not change because the bus is at rest in position. It does not move. And then it travels at a higher constant speed. So again, a linear section again, but this time the slope has to be higher than before. So how do we draw a higher slope? So it just has to be steeper like this. So if you can notice the difference between these two lines, they're both positive slopes, but this one is less steep than this one. So this is the idea here of higher constant speed. If you have a higher slope, then you have a steeper line. So therefore, this would be what the correct final answer looks like. An airplane of mass 2.5 times 10 to the power of 5 kilograms lands with a speed of 62 on the horizontal runway at time t equals 0. The airplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 at t equals 35. At t equals 35, the airplane stops decelerating and moves along the runway at a constant speed of 6 for a further 15 seconds. On figure 1.1, sketch the shape of the graph for the distance traveled by the airplane along the runway between t equals 0 and t equals 50. You are not required to calculate distance values. So let's see what the graph looks like and attempt to explain what's going on. So first of all, we have two sections here. Let's start with the t equals 35 section because it's easier. The airplane stops decelerating and moves at a constant speed for 15 seconds. So from 35 to 50, we have constant speed, and we said that for distance, the speed is the slope. So therefore, we have constant slope. So since we have a constant slope or gradient, therefore, the section has to be linear. So this section here is a straight line starting 35. It doesn't matter what the slope is, that doesn't really matter. But for the first section, it is decelerating uniformly. So how does that look like? So if something is decelerating, that means that the velocity is decreasing. And since the velocity is decreasing, we say that the slope or the gradient of the graph is not constant and it's decreasing. So not constant means that it's a curve. And decreasing means that it's concave down, it's frowning, not smiling. So in the previous questions, our graphs looked like this. This was concave up. But in this question, our graph will look more like a frown because it's decreasing, not increasing. So therefore, in the first section, we have a concave down curve like this. And they are supposed to continue here smoothly because the value of the speed did not change. So at a constant speed of 6. So since both of them were 6, you cannot, for example, draw something like this. So this, what I'm about to draw is incorrect. You cannot draw this section here like this and then something like this, for example. Because here, this gap here is incorrect. It has to move smoothly, has to continue smoothly at this point because both values of speed are 6. So watch out for that as well. The second part of our video has to do with analyzing graphs. So we're not going to graph here. We're just going to look at the given graph and analyze what's going on. So figure 1.1 shows a distance time graph for a cyclist traveling between points P and V on a straight road. Describe the motion between Q and R. So remember, we're going to do the other way around. We're going to follow the reverse logic. From Q to R, what's going on? From Q to R, this is a constant slope, right? And we said that the slope here is the same as the velocity. So therefore, from Q to R, we have constant velocity. Between R and S, we have a curve and it's frowning, not smiling. So this this is a smiling curve because it belongs to a smiling face, and this is a frowning curve because it belongs to a frowning face. So this would be acceleration, and this would be deceleration. Positive, increasing velocity, and decreasing velocity. So between R and S, we know that we have deceleration because we have a frowning curve. And finally, for S to T, the distance doesn't change at all. So this is zero slope, so the velocity is zero. And that tells us that the bus or the cyclist, excuse me, is at rest. So let's check the answers out. Like we said, from Q to R, this is a line, so it's constant speed. From R to S, it's frowning, so it's decelerating. And from S to T, it's constant distance in a sense, or like it stops, it's at rest, it's stationary. At rest and stationary mean the same thing. This is another question tackling the same issue. A bus is traveling between points A and D. There are bus stops at A, B, C, and D, but the bus does not stop at B and C. Figure 1.1 is a speed time graph. Describe the motion of the bus between each of the bus stops. Select the appropriate description from the list below. So between A and B, remember this is a speed time graph here. So here the slope is the acceleration itself. So this is different from last question, because in the last question, it was a distance time graph. So the slope was velocity. Here it's a speed time graph. So the slope is the acceleration. So from A to B, is the slope constant or changing? From A to B, the slope is changing. So it's definitely changing acceleration. So it's not constant. Is it increasing or decreasing? It's frowning, so it's obviously decreasing acceleration. So let's look at the answers. For A and B, it is decreasing acceleration because the curve is frowning. Now let's look at B and C together. B and C, we have here constant speed or zero slope. So acceleration is zero, the slope is zero because it's a horizontal line. And therefore, the speed is not changing. So we're going to write moving at a constant speed as the correct answer. Finally, from C to D, we have a straight line. So the slope is constant. And since the slope is constant, and the slope here is the acceleration, so the acceleration is constant. So therefore, we're going to write constant acceleration for part 3. So the trick is to handle this mathematically first. So from A to B, you have decreasing slope. And from B to C, you have zero slope. And from C to D, you have constant slope. And then depending on the graph, you would translate the slope into a physical quantity. So here the graph is speed. So here instead of slope, I write acceleration. So let's continue. Figures 1.1, 1.2 show speed time graphs, each moving in a straight line. Describe the motion of the object shown by the graph in figure 1.1. So in figure 1.1, this is a constant slope again. And figure 1.2 is a decreasing slope. And then we look at the graph and we translate slope into a physical quantity. So here the graph is a speed time graph. So the slope would be the acceleration. So we cross out slope and write acceleration. And therefore, in the first one, we have uniform or constant. Uniform and constant mean the same thing. So constant acceleration for the first one, decreasing acceleration for the second one. Excuse me. So define acceleration. We already said this is the change in velocity per unit time. And we want to describe the motion shown by each graph. So let's again analyze mathematically first. So mathematically here, this is constant slope and also negative slope. So this would be useful here as well. Here we have increasing positive slope. Here we have constant positive slope. And finally, for C, we have decreasing positive slope. Next, we remove the word slope and we write the physical quantity. So this is speed. So therefore, instead of slope, I can write acceleration. For B as well, this slope becomes acceleration. For C, this is a distance time graph. So instead of slope, here I have velocity. And for D as well, it's a distance time graph. So I can write velocity as well. Now I have everything I need to write the answers down. For A, we have constant negative acceleration. So this would be constant deceleration. For B, we have positive increasing acceleration. So I can just write increasing acceleration here. For C, we have decreasing positive velocity. So decreasing velocity, if the velocity is decreasing, what does that tell us? Decreasing velocity or just deceleration. So either we write decreasing velocity or we can write deceleration. Finally, in IV or graph D, we can write constant speed or constant velocity. Let's check the correct answers. So constant deceleration, followed by increasing acceleration, followed by decreasing speed or deceleration. And in IV, we have constant speed as we said. By the way, as a definition of acceleration, either you write change in velocity per unit time, or you write rate of change of velocity. So the word rate is exactly the same as per unit time. These both mean the same thing. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.